In this video we will see the evaluation of the definite integral of this type, integral 0 to 2 pi and a function of cos theta and sin theta d theta, right? The importance of residue will be seen in this lecture also, right? We'll try to convert this integral into a complex integral where we'll again use that theory of residues, right? Okay, so let capitalize this integral 0 to 2 pi f cos theta sin theta d theta. You can see that this is a definite integral with the limits 0 to 2 pi and the function is precisely of cos theta and sin theta, right? Okay, so what I will do, will substitute, put z equal to e to the power iota theta, so that dz equal to iota e to the power iota theta d theta, right? And from here you can easily find the value of d theta, that will be equal to dz over iota e to the power iota theta, and that is equal to z, right? So ultimately d theta will be equal to dz over iota z, and this is z equal to e to the power iota theta, right? So using this substitution, this integral will be converted, I is equal to integral f, right? And you know that the formula for cos theta is e to the power iota theta plus e to the power minus iota theta over 2, right? And sin theta can be written as e to the power iota theta minus e to the power minus iota theta over 2 iota, right? And this d theta is d theta, okay, 0 to 2 pi. And when we use this substitution, z equal to e to the power iota theta, this is actually a circle, right? With angle 0 to 2 pi, theta varying from 0 to 2 pi, right? So we can replace this integral by the contour integration c, where c is actually mod z equal to 1. This is equivalent to the unit circle centered at origin and radius equal to 1, right? And everything inside the function can be written as f, this will be z plus z inverse over 2, because this e to the power minus iota theta will be z to the power minus 1, and here z minus z inverse over 2 iota, and d theta will be replaced by dz over iota z, right? So ultimately the problem of evaluating the integral of this type, cos theta sin theta type, will be ultimately converted to evaluate a contour integration along this circle, right? Okay, and to evaluate this we will again use that theory of residues, right? Okay, so I will start with the examples. So you have to remember this thing, this convergence, right? Okay, taking example number 1, prove integral 0 to 2 pi. In most of the questions you will see that the integral limits of integration will be 0 to 2 pi, right? And if they are not 0 to 2 pi, we will convert them in 0 to 2 pi, right? Okay, so d theta over a plus b sin theta is equal to 2 pi over under root a square minus b square, right? And the relationship between a and b is given. The mod of a is greater than mod of b. A and b are complex numbers, right? Such that the modulus of a is greater than the modulus of b. Okay, so you can see that this integral has limits to 0 to 2 pi, and the function is of cos theta and sin theta. However, cos theta is absent here, right? So what we'll do, we'll use these substitutions. Solution, let, should I write, put z equal to e to the power iota theta, and then d theta will be ultimately equal to dz over iota z using this, right? And sin theta will be replaced by this thing, z minus z inverse over 2 iota, right? So that the integral is transformed to capital I equal to integral over c, right? And this c is actually mod z equal to 1, right? I will write that d theta will be replaced by dz over iota z a plus b, and the sin theta will be replaced by this b over 2 iota z minus z inverse, and z inverse is actually 1 over z, right? And this c is actually the unit circle centered at origin, right? Now we'll evaluate this before finding the residue, we have to first convert this denominator into a nice algebraic polynomial form, and that can be done by taking LCM. And this eta will be cancelled, I think, and 2 will appear here, okay, and I think dz over eta z, and z will be cancelled, okay, that will give me bz square, right, and minus b and 2a eta z, 2a eta z, right, and that z is cancelled, eta is cancelled, 2 appears here. So be careful at this step while taking the LCM in the denominator, okay. So this is a c, right, okay, so c is mod z equal to 1, okay. You can see that the poles or singularities of the function can be obtained by equating this denominator equal to 0, right. So put denominator equal to 0, put bz square plus 2a eta z minus b equal to 0 to get singularities, okay, and to find its roots we will have z equal to minus 2a eta plus minus b square, square of this thing, that will be minus 4a square, and I think plus 4b square over 2b, right. And then since we know that mod a is greater than mod b, right, so it should be written as a minus eta should be taken common, so that we'll get a square minus b square, because mod of a is greater than mod b, right. So ultimately that 4 will be cancelled. Ultimately I will be having minus of a eta, and here will be plus minus eta will appear outside, and a square minus b square over b, right. As you know that modulus of a is greater than modulus of b, that is given here, right. So I have changed their sign, and since minus eta was taken common, that appears here in form of eta. So this is a z, two values of z. Now it remains to decide that whether these poles, obviously they are poles, right, because the numerator, you can see the numerator, that is a constant function, analytic function, and the denominator is 0 at these points, right, and both of them are simple poles. Why we are calling them simple? Because their multiplicity is 1, right, being an algebraic polynomial in the denominator, right, these zeros of denominator are simple zeros, so the whole function has simple poles, right, are simple poles, right. And now I will check that whether these two poles lie inside our contour or not, right. So we have two poles here only. The first pole, let it be alpha minus a eta plus eta under root a square minus b square over b lies inside C, right. So this is a good point. How will you decide that one pole lies inside C or outside C? Out of these poles, only the first pole, the pole having plus sign, right, lies inside C. The reason is that if you apply modulus of this alpha, you will get some number which is less than equal to 1. I am writing the reason as mod of this alpha, mod of alpha, and if you take mod of some number, and you can see that it is a purely imaginary number, eta is appearing in both, or should I write it as eta here, eta here, right. So if you take modulus of this alpha, this eta will be eliminated, because modulus of any purely imaginary number is equal to the number with eta removed, right. So I will be having minus a plus b plus a square minus b square over b, right, is less than 1. We know that this thing is less than 1. And why we are claiming that this number is less than 1? Because if this is less than 1, I assume that this is less than 1, so I can take this a plus b on the right hand side, and that will be greater than under root of a square minus b square over b, right. Okay, then squaring both sides, squaring both sides will give me 1 plus a square over b square plus 2a over b greater than a square over b square minus 1, right? And you can see that this term will be cancelled out, and ultimately we will be left with the 2a by b, and I think that will become a by b greater than minus 1, right? Okay, or you will obtain a is greater than minus b, right? And that is obviously true, because you know that modulus of a is greater than modulus of b. It means that a should be greater than minus b, right? Okay, is true, right? And so we can say that this alpha, whose modulus is less than 1, should lie within this circle mod z equal to 1, right? Okay, so now I will find the residue at this pole alpha, and we'll apply that Cauchy's residue theorem, right? That is 2 pi iota multiplied by summation of residues. Okay, therefore residue, right, of my function at the pole z equal to this alpha. I am not writing that full alpha. This is my alpha, right? That is, since it is a simple pole, so I can use that formula. Means the numerator. Here is the numerator. See this function, right? We have 2 here. Should I write this 2 here? 2. Okay, 2, and we differentiate the denominator as we are having a simple pole, right? So differentiation of this will give me 2bz, and in place of z I have to substitute alpha and 2a iota plus 2a iota, right? So I think 2 will be cancelled out, and I will be left with 1 over b times of alpha. And what is my alpha? This is my alpha. If I multiply it by b, I will get minus a iota and plus iota under root a square minus b square, and this is my a iota plus a iota. So a iota will be cancelled out. I will be left with 1 over iota under root a square minus b square, right? So this is my residue at this simple pole. Now I will apply that Cauchy's residue theorem. Therefore, by Cauchy's residue theorem, the value of the integral I is equal to 2 pi iota multiplied by this residue. If you multiply this by 2 pi iota, you will get this result. I think where is that? 2 pi over 2 pi iota into residue fz z equal to alpha, and that will be equal to 2 pi over 2 pi over under root a square minus b square. So this is the required result, right? So the ultimate idea is to convert the integral of this type into a complex integral, and the contours should be especially mod z equal to 1, right? And then we apply the theory of residues, and then finally Cauchy's residues theorem, right? I will take another example, and this time I will take cos function in the numerator, right? The integral evaluates 0 to 2 pi. I am writing cos 3 theta here, right? What happens when we have some cos or sine functions in the numerator part, right? And the denominator is 5 minus 4 cos theta, and this is equal to pi over 12, right? You have to prove it. You can see that first thing is that the limits are 0 to 2 pi. That is a very good thing. But since we have this function present here, right? So if I use the same procedure as I used here, I will replace this by cos 3 theta is equal to e to the power iota 3 theta plus e to the power minus iota 3 theta upon 2, right? And if I write that in terms of exponential function, especially the numerator part, I will be having z cube plus 1 over z cube in the numerator, right? And on taking LCM, that will produce I think z cube in the denominator also, because z cube plus 1 over z cube, if I take the LCM, that will produce z to the power 6 plus 1 in the numerator, and ultimately in the denominator I will be having a z cube here, right? And that will go into my calculation, and to find the residues, that will be difficult, right? So be careful at this point when you have this function cos or sine in the numerator part. Rather you should apply a simple approach, and that approach is solution. You should just focus on this part. You know that we know that actually e to the power iota 3 theta is equal to cos 3 theta plus iota sine 3 theta. You know this thing, or should I write it for general, k theta? Okay. Then, or a real part of e to the power iota k theta is equal to cos k theta, this is the real part, and imaginary part of e to the power iota k theta is equal to sine k theta, right? So this information should be used in this numerical, right? And this is for all numericals whenever you have this cos or sine function in the numerator, right? So what I will do, I have since cos 3 theta, I will replace it by real part of e to the power iota 3 theta, right? Okay, and that is just to ease out the calculations. You can also start with this cos 3 theta, but that will make you a trouble, right? Okay, so then our I can be written as integral 0 to 2 pi, right? And real part, I can take real part here, real part of e to the power iota 3 theta and 5 minus, I should write real part here, a real part of e to the power iota 3 theta and d theta 5 minus 4 cos theta, right? Okay, so what I will do, I will evaluate it now using, since put e to the power iota theta equal to z, the same thing, and d theta will be equal to dz over iota z, right? And you know that since this cos theta is actually equal to e to the power iota theta plus e to the power minus iota theta over 2, right? Okay, so this will become then I equal to c, and I should write real part here, real part, or should I write it here, real part of this integral, and that will become, I think, z cube over that 2 and 2 will be cancelled. I will be left with 5 minus 2 z over 1 over z, okay, and this will be dz over iota z. So be careful at this point because there are so many z's, right? So after taking LCM of the denominator part, I will be having, I think, 2z square. This real part is here, a real part, okay. Z will be cancelled out. I think this z will be cancelled with this thing. I will be having z cube in the numerator. Dz iota is also there, so I will write iota. Where should I write iota? 1 over iota, or should I write iota here? Over iota. Okay, fine. And over this will become 2z square minus 2z square, and then minus 2, and then 5z plus 5z, right? Okay, and if I rationalize with iota, then I will be having minus iota in the numerator, and it will become plus, right? So it is inside the integral sign, integration c, right, where c is the unit circle mod z equal to 1, right? Okay, so I don't want this minus sign here. To remove this minus sign, I should write it as the real part of integral minus iota z cube dz over 2z square minus 5z plus 2, right? Okay, now this is c, and may I factorize it? 4, this will become minus 4 and minus 1. Okay, it is factorizable. So put denominator equal to 0 in order to find poles. 2z square minus 5z plus 2 equal to 0 to get poles. Obviously there will be poles, right? And that will give me 2z square minus 4z minus z plus 2 equal to 0, right? And that ultimately gave me z minus 2, and from here I'll be having 2z minus 1 equal to 0, right? Okay, so minus 4, okay, fine, that's fine. So this will give me z equal to 2 and 1 over 2 are simple poles, right? Now I have to decide whether these poles lie inside my circle or not. You can see that this z equal to 2, this will obviously lie outside the unit circle. Only this pole z equal to half will lie inside our contour C, right? Okay, before that I have to rub this. Only z equal to half lies inside C, right? So I will find residue at this point, a residue of function at z equal to half is equal to, since it is a simple pole, I will use that derivative formula. Where is my fz? This is my fz, right? So writing the numerator part as it is and differentiating the denominator, and then I will plug z equal to half. So minus eta z cube, this is the numerator part, and differentiation of the denominator, that will give me 4z minus 5, and then I will plug z equal to half here, right? So plugging z equal to half here will give me, I think that will become 2 minus 5, that will be minus 3, right? Okay, that will become minus 3 in the denominator, and here I will have minus eta over 8, okay, and that will ultimately become eta over 24, right? And then I have to multiply it by 2 pi eta, right? And 2 pi eta will produce, okay, but that will produce negative sign. I think something is wrong, because the answer should be pi over 12. So if I multiply this by 2 pi eta, where is my integral? This is my integral. Yes, this one, okay. And yeah, at this point I rationalize with eta, okay. At this point rationalize with eta and got minus eta, and okay, this minus is taken in the denominator, this minus is extra, okay, minus eta, okay, then it will become minus eta. Therefore, using Cauchy's residue theorem, I will get I equal to 2 pi eta multiplied by my residue, and that will give me answer, right? Pi over 12. Okay, taking another example, this time I will rather taking limits 0 to 2 pi, I should take limit 0 to pi, right? What happens when limits are from 0 to 2 pi? Ultimately we have to convert those limits into 0 to 2 pi, provided the function should be an even function, right? So okay, example number 3, prove I equal to 0 to pi, right? And d theta over a square plus sine square theta. You can see that the limits are from 0 to pi, and we have a here, right? You have to evaluate this value, or should I write it as pi upon under root 1 plus a square, right? Okay, and what about this a? I should assume that this a is greater than 1, okay, mod a is less than 1 or greater than 1, less than 1, okay, fine. We are assuming that mod of this complex number a is less than 1. And since limits are 0 to pi, so I cannot apply the same theory here. The limit should be strictly 0 to 2 pi. First, you should take care of this thing. This is pi, it should be 2 pi, right? In order to get 2 pi here as the upper limit, I will apply sine square theta should be replaced by 1 minus cos 2 theta by 2, and then I will use 2 theta equal to 2 t substitution. Solution: I equal to 0 to pi a d theta over a square plus, and it can be written 1 minus cos 2 theta over 2, right? And after using this formula, if I substitute 2 theta equal to t, right, then my problem will be resolved. It will become 0 to 2 pi. That is all we wanted, right? Put 2 theta equal to t, so that d theta will be replaced by dt by 2, and you can see that your limits will also be changed. The lower limit is 0. If you plug your lower limit here, you will get t equal to 0, and if you plug your upper limit here, you will get t equal to 2 pi, because theta equal to pi. So limits now are 0 to pi, right? And okay, here we will have a d theta, or d theta is replaced by dt by 2, so it will become dt over 2, and in the denominator we'll be having a square plus 1 minus cos t over 2, right? Or should I remove this 2 by taking LCM? It will become 2a square, and this 2 will be removed, right? Okay, now I will use my previous procedure. Put e to the power iota t, this time t, because we have t here, not theta. E to the power iota t is equal to z, and that will give me dt equal to dz over iota z, right? And where c becomes mod z equal to 1, right? Okay, so I will get I equal to, and this will become c mod z equal to 1. This a dt, a is a, dz over iota z divided by 2a square plus 1 minus cos t. Cos t is actually z plus 1 by z, z plus 1 by z. So ultimately you have your integrand in terms of z, right? Now taking LCM and simplifying it, we will get, I think this will become 4a square. First thing is that 4a square, and this will become 2, no, 4a square z, sorry, 4a square z is also there, 4a square z. Okay, this will become 2z, okay, 2z, and it will become 4a square plus 2z, okay, and the constant term is minus 1, and where is the z square term? That will be minus z square, so be careful at this point. Okay, 2 times of 2z times 2a square plus 1, that is fine, minus 1, okay, and where is that, z square, yeah, z square, fine. And you can see that dz over iota z, I want to get rid of this minus sign, so I will change these signs and I will write iota dz on rationalization, and this z will be, I think z was cancelled with this, okay, fine. And here we'll have a, and changing the sign, minus, and this will become plus, okay. Now it appears correct to me. Finding poles, right? Poles are given by equating denominator to 0, right? Okay, that will give me z equal to 4a square plus 2 and plus minus b square, okay, that will be square of this thing, 4a square plus 2 whole square and minus 4ac, okay, over twice of a. I think this will give me 16a to the power 4 plus 16a to the power 4 plus 4 and 4 will be cancelled out, right? And 8 4 4 16, okay, 16a square, something like this. So we'll be having 4, I think 4a square plus 2, and it will be plus minus, and we'll have inside our square root this thing, so 4 will appear out, I think 4a square, then 4a, okay, and ultimately we'll be left with a square plus 1, right? And here in the denominator we are having 2. So after cancellation we'll be having 2a square plus 1 plus minus 2a square root of a square plus 1, right? Okay, now we have to decide that whether these poles lie inside our circle or not, right? And what is a? Where is that a? Modulus of a is less than 1. Okay, so obviously if I take positive sign, then positive will be a big number as compared to plus and minus, right? So I will go to negative sign, and let us see that what happens if I take the second pole that is inside C or not. Clearly I'm writing here that I'm claiming that second pole, right, beta 2a square plus 1 minus twice of a under root a square plus 1, that lies within my contour C, right, lies inside C, and why I'm writing this as modulus of beta, I should take its modulus. And what is its modulus? Okay, it is a real number obviously, because a is less than 1, this is positive, that is okay. Less than 1, as modulus of b is less than 1, okay, gives me 2a square plus 1 minus twice of a under root a square plus 1 less than 1. We are assuming that this is less than 1. Hopefully it is true, and if it is true, then it will give some supporting fact, right, not a contradiction. So I will cancel this 1 and 1 obviously, okay, and that will give me 2a square minus twice of a under root a square plus 1, and that will be less than 0, right? And this will be taken on the right hand side, that will produce 2a square less than 2a under root of a square plus 1. I am hoping that I would get something mathematical fact that is obviously true in order to prove this true. If this is true, then we will get something that is mathematically true, right? Okay, then 2 and 2 can be cancelled out. Okay, and can a and a be cancelled out? Yes. A is, what is a? Where is a? A is modulus of a is less than 1. Less than 1. Okay, that can be cancelled out. So I will be having a less than under root a square plus 1, and that is obviously true. You can see that for any real number, right, it is less than its a square plus 1. You can check it. Okay, or I should square it in order to make it more perfect. A square less than a square plus 1, right, on squaring, or you will get, finally you will get 0 is less than 1, a mathematically proved fact, right? We know that 0 is less than 1, so this is true. It implies that this is also true, right? True, right? So beta lies within C, and obviously alpha will lies outside. And why we are saying so? Because alpha will lie outside. You can see that this equation has two roots, alpha and beta, right? One lies inside the circle, one has magnitude lesser than 1, the other will have magnitude greater than 1. I will prove it rather, since product of roots is equal to C upon A. From quadratic equation, C upon A, that will be equal to 1, that is, or alpha beta equal to 1. If I apply modulus, mod of alpha beta equal to 1, right, or mod of alpha mod of beta equal to 1, or mod beta equal to mod over 1 over mod alpha, right? And since, where is that, sorry, alpha, this is beta. Since you know that mod of beta is less than 1, so reciprocal of mod beta will be greater than 1, right? So this will be greater than 1, because mod beta less than 1, if you take the reciprocal of this thing, you will get 1 by mod beta greater than 1. So this is what we got, right? So alpha lies outside C and beta lies inside C. This is a small proof for alpha. In order to prove that alpha is really lying outside your circle. You can prove this, you can use this fact in the previous examples also. Therefore, alpha lies outside C. Okay, alpha is the root with negative sign, right? Should I write it here? Where alpha equal to 2a square plus 1 and plus 2a the root a square plus 1. Okay, so we are interested in beta only. Therefore, residue of fz at z equal to beta, that will be equal to, where is my function? This is my function. Okay, a iota over differentiation of denominator, that will be 2z minus 4a square plus 2, and in place of z I will write beta. Okay, so this is the value of beta. You plug it here, a iota over, okay, I am not missing any sign, yeah, that was a iota. Okay, if I plug beta here, then twice of beta will be 4a square plus 2 minus 4a square minus 2. Something is wrong, so everything is getting cancelled, that is not correct. Square root is also there, sorry, twice of beta, okay, minus 4a square root of a square plus 1, and this is minus 4a square minus 2. So 4a square will be cancelled, 2 and 2 will be cancelled, and we will be left with minus iota over 4 under root a square plus 1. By using Residue's theorem, I is equal to 2 pi iota multiplied by this only residue minus iota over 4 under root a square plus 1. Hopefully I am getting the correct answer. 2 pi by 2 pi by 2 under root a square plus 1. Was it the answer? Where is that? This 2 was not there. I missed 1 2, I think. Yes, 2 was there. This 2. So that should appear here. 2 goes here. 2a. Now it is correct. You see that it becomes z square. That is fine, and that is also fine. Plus 1. It appeared from where? Plus 1. From here. Okay, right. Should it be plus 1 or plus 2? Because that was 2. If I take the LCM, then it will 4a square, that is correct. Okay, this term is correct. And this will become minus z square. This will become minus 1. Okay, that is fine. Okay, now it is fine. So this 2 was there. I missed this 2 in the numerator part. So I am having 2a iota, and now it will become by 2. Okay, 2 and 2, and finally we got the correct answer, right? So be careful at this point. Take your time to evaluate this step, right? Okay, so we have done how much examples? 3 examples. One more example I will take, and example number I think 4, right? Prove, or should I write evaluate this time? Evaluate integral 0 to pi. Again I am using those same limits, 0 to pi. 1 plus 2 cos theta, 5 plus 4 cos theta. You can see that the numerator and denominator are both containing cos function, right? D theta. And again you see this upper limit, it should be 2 pi, as we have seen in the last example. We made a substitution of sin square theta, this is 1 minus cos 2 theta upon 2, and finally we got the 2 pi in the upper limit, right? But here we cannot use the same method because there is no cos square theta or sin square theta, right? Okay, so what I will do, I will focus on this integrand. You just focus on this integrand, is it an even function or odd function? You can see that if you replace theta by minus theta, you will get the same thing. 1 plus 2 cos of minus theta divided by 5 plus 4 cos of minus theta, and that will be ultimately equal to 1 plus 2 cos theta over 5 plus 4 sin theta. It means that this integrand is an even function, right? An even function of theta, right? So if it is an even function of theta, I can write it as I is equal to 0 to pi 1 plus 2 cos theta over 5 plus 4 cos theta d theta. We can write the limits 0 to 2 pi and balance with 1 by 2, right? 1 plus 2 cos theta, 5 plus 4 cos theta, right? And this step is valid if and only if this function is an even function, right? So ultimately I have got 2 pi in my upper limit, then I can use the same thing here. Okay, let z equal to e to the power iota theta, that will give me d theta equal to dz over iota z, where mod z equal to 1, and this will become I equal to 1 over 2, and it will become c, and if you focus on the numerator, 1 plus 2 z plus 1 by 2, and be careful at this step because we have 2 here also, so this 2 will be eliminated after cancellation, and in the denominator I will be having 4 plus 2 times, this 4 will become 2, and z plus 1 over z, and dz over iota z, right, where c is mod z equal to 1. Okay, now taking the LCM and simplifying it, I will get, I think, okay, I will write that here. I equal to 1 over 2 integral c, that will become z square plus z plus 1 over, yeah, that z will appear here, iota z will appear here, iota z, should I write that iota here, over iota dz, okay, and on taking LCM it will become 2z square and 5z plus 2, right? So this is your integrand finally, and you can see that poles will be given by equating denominator to 0, and poles are, I'm writing the poles directly, z equal to 0, that will be obtained from this one, and I think the factorization will be 2z plus 1 and z plus 2, 2z square plus z 4z, I think that is correct. Okay, so that will give you 0 and minus half and minus 2, right? And all of them are simple poles, right? Okay, now you decide that this minus 2 will lie outside the unit circle, obviously, or only these two poles will lie inside. So only this pole and this pole will belong to your inside your contour C. So I am finding residue first at z equal to 0, and then I will find residue at this point. And since both of these are simple poles, so I can use that derivative formula or alternate formula, limit z tends to 0, and this is z times this thing, z square plus z plus 1 iota. Iota is in the denominator, I think. Where is that? Yeah, d iota over iota, okay, over iota upon 2z square plus 5z plus 2, because this z will be cancelled, okay, and then I will plug 0 here, I will get 1 over 2 iota, I think, yeah, 1 over 2 iota, fine. And the residue of fz at z equal to minus half will produce, now I am using that derivative formula this time, the numerator as it is, z square plus z plus 1 over iota, and the differentiation of denominator, so multiply this by 2, this z inside, you will get 2z cube, and differentiation of 2z cube is 6z square, and this is 5z square, so it will become 10z. So it will become 2z, so it will become 2, and then I will plug z equal to minus half here, right? Okay, so plugging minus half here, it will become 1 by 4 plus 1 by 2, so that will become 1 by 4 plus 1 by 2, that will become 3 by 4, I think, 3 by 4 iota, okay, over, that is 6 by 4, 6 by 4 means 3 by 2 minus 5 plus 2, minus 3, okay, on taking LCM it will become minus 6 minus 3 by 2, minus 3 by 2, and this 3 and 3 will be cancelled out, so ultimately 2 will be cancelled out, I am left with minus 1 over 2 iota, right? Okay. Okay, they are opposite in sign. So finally I will be getting 0 as answer. Therefore, by residue theorem, I equal to 2 pi iota multiplied by sum of residues. This time I am having two residues. One is at z equal to 0 and the other is at z equal to minus half, right? So adding these I will get 0, right? So this is the value of the integral. Example number, I think, 5. Prove or evaluate integral 0 to 2 pi cos n theta d theta over 1 plus 2a cos theta plus a square, right? So you have to evaluate this integral, and you can see that in the numerator you are having cos n theta, right? And I should add one more thing, and it's sin n theta over 1 plus 2a cos theta plus a square d theta, right? Okay. So again we have cos in the numerator if you focus on the first part. So I will replace this by a real part of e to the power iota n theta, right? And information about this a, the a is less than 1, mod of a is less than 1, okay. Solution, let I equal to e to the power iota n theta over 1 plus 2a cos theta plus a square d theta. I have assumed that the numerator is e to the power iota n theta, right? And I will evaluate this I, and after getting this I will take the real part to get the answer for first part and take the imaginary part to get the answer for second part, right? Okay, so I have replaced the numerator by e to the power iota n theta. You can do this by this approach also, right? Rather than writing is real part of this, right? You should first replace the function by exponential function, and at last we'll compare the real and imaginary part to get the answers, right? So let's consider this integral. I should write it as consider a new integral of this nature, right? Okay, 0 to 2 pi, the limits are fine, 0 to 2 pi. So put e to the power iota theta equal to z, that will give me d theta equal to dz over iota z, and my c becomes mod z equal to 1. So it will give me I equal to c z to the power n, I think, yeah, and dz over iota z, and in the denominator we have 1 plus 2. This 2 will be cancelled by the formula of cos theta. I will get a z plus 1 over z plus a square, okay. And now taking LCM of this thing in the numerator, I will write it here, c, I will get az square. The first thing is that az square, the second is z, okay, plus a square, so a square plus 1z, and then constant term plus a, okay. And in this part z and z will be cancelled out, and this will become z to the power n over iota dz, okay, fine, okay. Now finding the poles, right? So poles are given by equating denominator to 0, right? And from here I will get this will give me z equal to minus of a square plus 1 plus minus square root of b square minus 4ac over twice of a. Okay, and if you evaluate this, you will get a to the 4 minus, that will become a square minus 1 whole square. Okay, that will give me minus of a square plus 1 plus minus a square minus 1, right, over 2a, right? So this is my z, and that will give me two poles. One I will let alpha, and if I take plus sign, then minus a square plus a square will be cancelled out. Minus 1 and minus 1, that will be minus 2, right? And that will be minus 1 by a, I think 1 by a. And beta will be, if I take negative sign, that will give me minus 2a square upon 2a, will be minus a, right? So these are my two simple poles, or simple poles, right? Now we have to decide that whether alpha or beta lies inside C, right? You can see that modulus of A is less than 1, so I will apply modulus for these. And now modulus of A will be equal to 1 over A, obviously 1 over mod A, and you know that mod of A is less than 1, so reciprocal of 1 mod of A will be greater than 1, so this will be greater than 1, and mod of beta is equal to mod of A, that is less than 1, that is given in question, right? So ultimately alpha lies outside C and beta lies inside C. Therefore beta equal to the second pole minus A lies inside C, right? Okay. Now residue. Therefore residue of function at z equal to minus A will be given by, it is a simple pole obviously. Where is my integrand? Yeah, this is my z, right? Okay. So z to the power n over eta upon differentiation of this thing, because it's a simple pole, that will give me 2az plus a square plus 1, and then I will put z equal to minus a here. On putting z equal to minus a, I will be getting minus a to the power n over eta, yes, and this will become minus 2a square plus a square, so ultimately that will be 1 minus a square, right? And yes, so this is my residue. Therefore the value of integral is actually equal to 2 pi eta multiplied by summation of residues, and since there is only one residue, I have z at z equal to minus a by residue theorem, right? For multiplying this by 2 pi eta, I will get 2 pi, eta will be cancelled, you will get minus a to the power n over 1 minus a square, right? So, or you can write it as 2 pi minus 1 to the power n, a to the power n over 1 minus a square. So this is I, capital I, and you remember that your capital I was this integral, but your target is to evaluate this integral, the cos n theta and sin n theta. So I will plug the value of I from there. I is actually, there is that I, integral 0 to 2 pi, and this is my e to the power eta n theta, and e to the power eta n theta can be written as cos n theta plus eta sin n theta, right, over 1 plus 2a cos theta plus a square d theta, right, and that is equal to this value, equal to 2 pi minus 1 to the power n, a to the power n over 1 minus a square, right? And you can now compare real and imaginary parts. Since the imaginary part is completely missing on the right hand side, you can see that there is no eta term, right? So equate real and imaginary parts on both sides. Left hand side will give you 0 to 2 pi cos n theta d theta over 1 plus 2 a cos theta plus a square equal to 2 pi minus 1 to the power n, a to the power n over 1 minus a square, And on equating imaginary parts, the left hand side imaginary part is sine n theta d theta 1 plus 2a cos theta plus a square equal to 0. You can see that the right hand side is containing 0 iota. The imaginary part is 0, so 0 times iota. So this is it for evaluation of the integral of this type, especially when limits are 0 to 2 pi and the integrand is containing the cos theta and sin theta functions, right? And in the next video we will be doing something more on application of residues, right? Again the definite integral but of the different nature, maybe the integration on real axis, right? That will be part of the next video. For this video, thanks.